Welcome to ICM-Online problem series in mathematics on real analysis. Problem number 7. Let f from Rn to Rn be continuously differentiable map satisfying norm of f of x minus f of y greater than or equal to norm of x minus y for every x comma y in Rn. Then f is onto or f of Rn is a closed subset of Rn, or f of Rn is an open subset of Rn, or f of 0 equals 0. Let us discuss the answer. First we observe that f is injective because f of x equals f of y implies norm of f of x minus f of y equals 0. From the given condition, it follows that norm of x minus y equals 0, which implies x equals y. Next, we claim that the total derivative of f, Tc, is non-singular at every point C. If Tc of v equals 0 for some non-zero point v in Rn, the condition that f of c plus v minus f of c equals Tc of v plus little of norm of v as v tends to 0. Actually, the condition is the definition of the total derivative implies that f of c plus v minus f of c equals little of norm of v, which implies f of c plus v minus f of c divided by norm of v tends to 0 as v tends to 0, which is impossible because from the given condition it follows that norm of f of c plus v minus f of c divided by norm of v is greater than or equal to 1. Thus, Tc of v is non-singular. Since Tc is non-singular, its matrix is also must be non-singular, that is, the Jacobian matrix should be non-singular. Now, let us recall a theorem. Let A be an open subset of Rn and assume that f from A to Rn is continuous and has finite partial derivatives on A. If f is 1 to 1 on A and if the Jacobian determinant jf of x not equal to 0 for all x in A, then f of A is open. From this result, it follows that option C is true. Next, we claim that the image f of Rn is closed. Take y from U, which is the complement of the image. If y is not an interior point of U, for each integer n in N, there exists a point xn in Rn with f of xn belongs to b of y 1 by n, which is the ball centered at y and having radius 1 by n. Then sequence f of xn is Cauchy, follows from the construction of the sequence f of xn, and this implies that sequence xn is Cauchy. This follows from the condition given. So there is x in Rn such that xn converges to x, since Rn is a complete metric space. Since f is continuous, this implies f of xn converges to f of x. But from the construction of the sequence, it follows that f of xn converges to y. Thus, y must be equal to f of x by the uniqueness of the limits, which is not possible because y is taken from the complement of the image. Hence, y must be an interior point of U, and this implies that U is an open subset of Rn. That is, f of Rn is closed. Therefore, option B is true. Now we have observed that f of Rn is both closed and open. And we know that Rn is a connected space. So, the only subsets which are both open and closed are the empty set and the full set. So, the image of f must be all of Rn. That means f is onto. Thus, we observe that options A, B and C are true and option D is false. Consider f from Rn to Rn defined by f of x equals x plus a, where a is a non-zero element in Rn. Note that f has all the required properties, but f of 0 equals a, which is non-zero.